Alright, hello, my name is James. I'm just going to do a quick review of the concepts of chemistry and biology, specifically focusing on basic biology, so I'm not going to go too in-depth into all the chemical properties, but just enough to hopefully help any of you who are listening to gain a better understanding of how chemistry plays an impact into biology. And so the first thing I want to do is I'm going to create a chart. So I'm going to add a table right here. Let's just make it like this for right now. So right here I'm going to put the atom or the element. So an element is anything that you can find on the periodic table. An element would also include two of the same atom that are bonded to each other, so like hydrogen gas. And so that's kind of what an element is. So the four elements I'm going to put on this chart is I'm going to put hydrogen, I'm going to put carbon, I'm going to put oxygen, and I'm going to add one more down here, which is going to be nitrogen. And these are the most common elements or atoms found in organisms. In fact, carbon, there's a whole section of chemistry related to carbon called organic chemistry. And so what we're going to do is we're going to kind of talk about their properties and then how they relate back to biology. So the first thing to understand with the atom or the element is their atomic number. So the atomic number is the number that they're assigned on the periodic table. Hydrogen has an atomic number of 1, carbon has an atomic number of 6, nitrogen is 7, and oxygen is 8. And this is basically the number of protons. So under here I'm going to put the number of protons. So this is always going to be a set number, you're never going to see any decimals. And the way to remember it is simply basically that hydrogen is really small, so you can have 1 proton. You'll see them in acids and bases where hydrogen is leaving and become a proton. So a proton is a hydrogen atom without its electrons. We'll talk about electrons in a second. Carbon has 6, which is really nice if you just remember 6. Oxygen is highly electronegative. So I'm going to put that term right underneath here, electronegative. And we'll talk about that term in just a second, so I don't forget to define it. And then nitrogen is in between carbon and oxygen. So you've got 7s between 8 and 6. The other number that you'll oftentimes see on a periodic table is important to understand when it comes to chemistry and biology is the atomic mass. The atomic mass is the sum of protons and neutrons. So neutrons are also found in the nucleus, but they are not charged. Protons have a positive charge, neutrons don't, but they do contribute to the mass of an atom. So hydrogen still has an atomic mass of 1 because it doesn't have any neutrons. It's just a proton with an electron in its electron shell. Carbon has an atomic mass typically of 12, but you also sometimes see an atomic mass of 13 and 14. So these are called isotopes. Isotopes, right here, they differ in atomic mass. And so carbon, for example, will still have 6 protons and a mass of 12, a mass of 13, a mass of 14, but the number of neutrons will be different. So an atomic mass of 12, the carbon atom has 6 neutrons, 13 it has 7, and 14 it has 8. 13 is not found very commonly. It's found in about 1% of carbon, and 14 is rarely found. It's actually radioactive, and so it's never really created. It's just destroyed over time. It just self-destructs itself. And so what you can use this number is, you'll see, look at the periodic table and you'll see something like 12.11. So 12.11 is the average atomic mass of carbon that you'll find. So oxygen has an atomic mass of 16, and nitrogen has an atomic mass of 14. And these are going to be helpful, especially during the exam when you're comparing sizes of molecules, compounds, atoms, as Professor Dawson often likes to do. So when I'm comparing sizes, typically Professor Dawson is referring to mass. And so you see the chart up here, this guy right up here, yep, right there. That's where your atomic mass is going to be when you're comparing sizes, the number of protons and neutrons. Electrons are kind of important, but they don't really weigh anything. They weigh about 1/2000th of the mass of a proton or neutron. And so say for example, Professor Dawson asks you to compare H2 or oxygen in terms of mass. So what you're going to do is, and she asks you which one has greater mass. So this hydrogen right over here, this H2, it's going to have two hydrogens bonded by a covalent bond. We'll talk about bonding in just a second. So that's going to be an H bonded to an H. So it's going to have a total mass of 2 AMU, or atomic mass units, 1 plus 1 from over here, 1. Oxygen, on the other hand, has an atomic mass of 16. So this is 16 AMU. So if she's going to ask for the greatest mass, oxygen would be your answer over here. If she's asking for the least mass, it's going to be H2. And so you can see that a molecule can have a smaller mass than an atom, which is really important. And so if we're going to talk about electrons, electrons have a negative charge, which is important to understand because you don't want to have charged atoms. So any atom that is neutrally charged is going to have the same number of negative charges as it does positive charges. And so what you're going to be doing is you're going to be matching this guy over here. So you're going to have 1 in hydrogen, 6 in carbon, 6 in carbon, 8 in oxygen, and in nitrogen we're going to have a total of 7. Yep. Awesome. And so these are the total number of electrons. The number of electrons are not important. I'm going to write that down here because it's not. Number of electrons is not important. However, the number of electrons in outer shell is important. And so we're going to add another column right here. Table. So electrons in outer shell. Let's leave these guys over here real fast. Oh. Electrons in outer shell. And also sometimes referred to as valence electrons. So these are the electrons that allow for reactions to happen there on the outside. So the number of electrons in the outer shell, important, is determined by the number of electrons that an element would like to have on the outside. So that's 8 minus so we got electrons. Okay. So basically for hydrogen carbon, it's going to be equal to the column number. Or if you really like math, it's going to be equal to the total number of electrons. So number of electrons minus 2 minus 8 times x, however many times you need to minus it. But your answer is always going to be positive. Always positive between 0 and between 1 and 8. It's going to be a total. So, for example, with hydrogen, if you take 1, it's minus 2 first. 1 minus 2 is negative 1. So we can't have that, so we're going to have 1 electron on the outer shell. It's also in the first column. Carbon has 6 electrons. So you take 6, and then we minus 2 first, so that gives us 4. And if we minus 8 from 4, we get negative 4, so we can't have negative numbers. So 4 is going to be our final answer for the number of electrons in the outer shell. Oxygen following 8, minus 2 is 6, minus 8 from that would be negative, and then 7 minus 2 is 5. So you do 5 electrons in the outer shell. And so what the number of electrons in the outer shell helps you determine, answer to the right, is the number of electrons, or the number of bonds that an atom wants to form. So the number of bonds is going to be equal to 8 minus electrons in outer shell, with the exception being hydrogen and helium, which is going to be 2 minus the electrons in outer shell. And that's just because hydrogen and helium are really small atoms, since they can only fit 2 in the closest orbital. If you think of it as kind of this cloud, in hydrogen your electrons are, so this is your nucleus, And then if this red is your electrons are kind of floating around in this area right here. And so it's really close, and we can only fit 2 because they're negative. And so after that, after you have 2 in the inner shell, so this also explains this 2 down here, your electrons get spread out a little bit more, so they kind of go like this. Just kind of nice where you have it shaped up and down, and kind of the tetrahedral shape, which I'll talk about shaping in just a second. But because it fits more space, you're going to have 8 in these outer shells around here. And so just to kind of simplify things, if you take hydrogen as our exception, so 2 minus 1 is 1, so you can have 1 bond. Covalent bond is specifically what it's talking about. We'll talk about that in a second. So carbon is 8, so none of these other ones are an exception to the rule. So 8 minus 4 is 4. 8 minus 6 is 2. And 8 minus 5 is 3. And so this is the number of bonds it's going to want to form. So I'm going to delete this guy real fast for us. And I'm going to draw something else. So let's use carbon as an example first. So carbon, this is the nucleus of the atom right here. And so this carbon has a positive charge. The nucleus is positive, and so the electrons are all negative. So they're trying to space themselves as far away from carbon as they can. And remember that we're in a 3-dimensional shape. So I'm going to put, I'm going to use green. So we're going to take this guy and we're going to put 2 electrons over here, because electrons like to be in pairs. Kind of like life, we like to find someone to be with. So we've got a pair of electrons over here. So the easiest way to do this isn't if we have a 2-dimensional shape. We kind of go in 3 dimensions. So I put 1 over here. And right now I'm going to draw all 8 because it wants to have 8. I have 1 over here. And then we're going to have 1, and this is in the back. And so each of these, the distance between here and here, is 109.5, which isn't important to remember that. But it's just to show you that there's 109.5 degrees between here, 109.5 between these two, between these two, between these two, and 109.5 is much greater than if we just had a 2-dimensional shape of carbon, and then we did boom, 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 and we're like, hey, we got 90 degrees. 90 degrees is way too close. 109 is much better. So this guy right here is wrong. Forget about that guy. Not good. So I'm going to delete this guy. Alright, and so that's kind of the shape. So if you were to put it into a pyramid, you'd have this triangle base, and then you'd go up. And so here's your pyramid, and then you'd have your electrons in each of these corners. And then you'd have your center part in the middle, and then you'd be forming bonds. Boom, 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 boom. And this is sometimes shown, I'm going to use methane as an example. So methane is just carbon with 4 hydrogens. As you have your carbon, still flat, is with the paper. So you have 1 with the paper, with a hydrogen up here. You have 1 with the paper over here. And you have some dashed lines like this, which means it's going behind the paper. So it's pushing backwards in the 3-dimensional shape. And then you'll have these triangles, these wedges, which means it's coming towards you. It's coming off the paper towards you. So that's kind of sometimes how they're drawn 3-dimensionally, which is kind of just to do with the shape. And so anyways, getting back onto the shapes of chemistry, if we delete all these guys real fast again, I'm not going to delete all of them, I'll leave them there for a second. The number of bonds is the ones that are able to form. So this one's carbon right here, it's got 4, and that's because carbon by itself has 4 electrons, and so 1, 2, 3, 4, and so when it forms with hydrogen, hydrogen likes to have up here 1 bond, and so we're going to form 1 bond here, form 1 bond here, 1 bond here, 1 bond here, and it's happy. And it doesn't have to be with hydrogen, it could form with another carbon. And if it wanted to, this carbon would bring 4, so 1, 2, 3, 4, and then it could form with another hydrogen, which would bring this one hydrogen, and we could put another carbon over here if we wanted to, so 1, 2, 3, 4, put a hydrogen up here, bond, hydrogen over here, bond, hydrogen over here, bond. So right here we have 3 carbons bonded to each other, and we have 8 hydrogens. And so the chemical formula would be C3H8. And if you look at this octet rule, you can see the C's got 1, 2, 3, 4, 5, 6, 7, 8. If you count this carbon right here, it's got 1, 2, 3, 4, 5, 6, 7, 8. So that's good, and the third one's the same. And then all the hydrogens, like we talked about up here, hydrogens want 2 electrons in the outer shell. So if you got 1, 2, 1, 2, 1, 2, and all the way around. So they're all happy and stable, because that's kind of where we want to be. And so you can draw it out with these dots right here if that's what helps you remember the octet rule, or anytime you see a bond, you remember that there's 2 electrons in this bond right here. So every bond has 2 electrons, and this is a covalent bond. So covalent bond is when they're sharing electrons. So if I was to draw kind of a graph right here, this is atom A, this is atom B. Covalent bond would be like anywhere in this section is where the electrons would be found, somewhere between there. And where they're found on there is determined by this electronegativity. So electronegativity is the affinity of the nucleus towards electrons. To simplify that down, it's just how much an atom wants electrons, how much it's going to take electrons, how much it's going to steal electrons. And so if you think about it, siblings, one stronger than the other, it's going to push back and forth. So the further it is to B, so say the electrons were over here in this covalent bond, then B is highly electronegative and A is less electronegative. If they're equal, so if they both have the same, the electrons aren't going to be found here, they're going to be found towards the center, which is really good. And these are just for covalent bonds. And so if I had my electrons over here, element B is going to be partially charged, so use delta. It's kind of like an O with a little eyebrow or something on the top. Toupee, I don't know. So B, because the electrons are closer to it, it's going to be slightly negative. And then because the electrons are further away from A, because A still has the positive charges from its protons, it's going to be slightly positively charged. And this is what's going to cause some partial charges. And just like a magnet, those partial charges are going to act against one another. So if I scroll down a little bit, I'm going to show how this kind of works with water. So water is written as H2O. So you have one oxygen up here, you have a hydrogen, and then this tetrahedral shape that I was talking about. So like, why are these hydrogens so close to each other? These electron bonds are so close. It's not as far as they could be. They could be 180 degrees apart. Well, they really can't be, because right up here you have a couple electrons, and you have a couple electrons in the back behind this paper over here. And so the distance between here, I mean, if you approximate it, it'd be about 109.5. It's actually going to be a little bit closer than that, because these electrons by themselves are going to push this guy closer together, which is going to give this oxygen a bent shape, because it's bent. So I'm going to erase these guys right here real fast again, because they're not important to see, because we've got their shape right here. So oxygen is highly electronegative. And how do we know it's highly electronegative? If the periodic table over here, the electronegativity is going to be determined a lot by the number of protons. I'm just going to draw some random charts. And so the more to the right you go, the more protons are in the nucleus. So the more protons you have in the nucleus, the more tightly it's going to pack those electrons. It's going to be able to take electrons. So your electron affinity is going to increase. So it's good stuff up here. And then for electronegativity, if you're comparing up and down the column, the electronegativity is going to increase as you move up. The reason why it increases when you move up is because these atoms up here, like fluorine, they're really small. And so when you add these extra electrons, they're going to be really close to this fluorine atom. So it's going to be this positive charged fluorine nucleus is going to be able to accept those really well. Whereas if you take iodine, you try to put some extra negative, like how negative this could be. It's this huge guy. And so it really could care less how much extra electrons or negativity it has, so it's going to increase a little bit less. And so diagonal is kind of impossible to compare this way. Can't really say. But if you're going to the right, you're increasing negativity, and as you're going up, you're increasing in electronegativity. And so oxygen is probably the most important one you can remember. Oxygen and nitrogen and fluorine are some of the most electronegative atoms on the periodic table, and probably the only ones you'll ever see in biology. And so because of that, this oxygen has more electronegativity. The electrons are going to be moved up closer to here on average. If you take a statistic probability, it'll probably be found right around there. And so this guy is going to be partially negative, and this hydrogen is going to be partially positive because electrons are moved further away, and same with over here. Now if we drew another water molecule, so we drew one right here, this oxygen is still going to be negatively charged, partially negatively charged, not fully charged, but partially charged. This hydrogen is still going to be positively charged. So what's going to happen is between this negative charge and this positive charge, we're going to have what's called a hydrogen bond. And a hydrogen bond just occurs because of the difference of electronegativity between these two. So that's just going to be this partially negative, partially positive, and then it can attach to other partially positive, partially negative. It's not going to exist something like a carbon, hydrogen. We'll just use methane as another example like we did last time. We had two methane molecules next to each other. We're not going to see that because carbon's not really highly electronegative. It's not oxygen, it's not nitrogen, and it's not fluorine, so we're really not going to care about carbon too much when it comes to electronegativity. So we're just going to get this guy off of here so we don't get any confusion. We'll just kind of delete this guy. There we go. Oh, still there. Alright, there we go. So these are hydrogen bondings. When you get to chapter 3, when you're talking about proteins and their shape, the hydrogen bonds are what's going to help them retain their strength. And you get things like temperature involved. What temperature is going to do is it's going to slow these molecules down. So these molecules right here are going to be moving slower than they were before, these ones right here. And as they move slower, this hydrogen bond that's outlined right here is going to become more solidified. And so what water is going to do is it's going to form a structure that keeps them more spaced out from each other. And that more spaced out structure, you can see right here, pretend these are hydrogen bonds, all of these solid lines, and the water molecules are in the peaks. This more structured model is going to put more space in between the molecules. It's going to make it less dense, which is going to allow ice to float on water, which is a really cool property. And then if you increase the temperature, the molecules are going to be moving faster. I'm going to delete this guy again. So the molecules are going to be moving faster, and this right here is going to break more frequently. And this breaking in proteins is what causes them to lose their shape, which is not good. The other thing that can cause them to lose its shape is if you have a higher or lower acidity pH. So pH is a measurement of the hydrogen ions or hydroxide ions in a solution. So the hydrogen ions are fully positive, so they're going to attach more of these oxygens than this other water is, and so it's going to break those. Hydroxide ions are going to have the same effect on the hydrogens, and so it's just not going to be good. But to explain, yeah, so that's basically what hydrogen bonding is, and electronegativity summed up. So hopefully that covers everything in that area. If you want to talk about something besides covalent bonding, you're talking about full charges. That's when we get into ionic bonding. So ions, will go up here, or when the number of electrons is different than this. So if I have more electrons than what an element typically has, I'm going to have a negative ion. So it's going to have a minus charge. If I have less electrons than what's presented right here, I'm going to have a positive ion. So typically the elements in the first 4 columns will have positive ions because it'd rather lose electrons in its outer shell until it's got a full outer shell. So it's much easier to give up 3 or give up 2, or especially to give up 1, than it is to gain, respectively, 5, 6, or 7 electrons. And the opposite's true for the other side of the periodic table. The last 4 columns are going to be the opposite. They're going to want to gain electrons. It's much easier for them to gain 1, 2, or 3 electrons than it is for them to lose, respectively, 7 electrons, 6 electrons, and 5 electrons. So it's just kind of to help simplify that process, which is really nice of them to do. And so when you have ionic bonds, they're going to easily separate. So the common example is sodium chloride, sodium positive, chloride negative. They're attracted to each other, so they've got strong attraction. This is really good. They're not sharing electrons because chlorine has an extra electron. Sodium doesn't have that electron anymore. And so when they're put in water, they can dissolve because of all of these hydrogen bondings down here. All these hydrogen bonds collectively, these partially negative charges, a lot of them can break up the sodium from this chlorine, and that's what dissolves your salt in your water. So it's a really cool effect. And I think that's really all I want to talk about when it comes to chemistry. If you have any questions, let me know, but I think that sums most of it up. So thanks for watching.